Good evening. My name is Rebecca and I'm with the Allegheny County Conservation District. Thanks for joining us for tonight's webinar, Water Quality Monitoring Basics with the Pittsburgh Collaboratory for Water Research, Education and Outreach. This webinar is being recorded and it will be posted on our website for future views along with our other recorded webinars from these past few months. We will follow up with a message tomorrow containing a link to the recorded webinar and further resources on these topics. This webinar is part 2 of a 4-part series, Advocating for Your Watershed. And if you haven't already, we hope that you register for more and also spread the word to others. This series is meant to give participants an intro look into some of the core activities undertaken by watershed or community groups and volunteers. You can find information and registration links on our Facebook page and ACCD website. Your dog, sorry. At the end of the presentations, we will have the opportunity to join breakout rooms based on one of the 3 larger watersheds. Sorry, it's automatically muting me. To talk more about smaller watersheds. This is a great opportunity to share issues, assets, possible sampling locations, and any of your personal efforts. Thanks to those of you who were already able to fill out the pre-webinar survey in advance. I can place you into rooms immediately. If you haven't shared your watershed with us, please let me know in the chat box and I can assign you to the correct room. Also, if you find yourself in the wrong watershed room, please let me know and I can get you to the right place. Also, please feel free to type questions in the chat box at any time and we will address them at the end of the presentations. Now on to the good stuff. We are grateful for our speakers for today's topic in this series. Megan Guy with Pitt Collaboratory will tell us more and make introductions. Okay, Megan, I'll stop share and pass it over to you.
Thanks, Rebecca. All right. All right, so hi everyone. My name is Megan Guy and I am with the Pittsburgh Water Collaboratory. We are an organization at the University of Pittsburgh that hopes to be a bridge between the research that's happening with water and the greater community. So our vision is to be that platform where science and community meet. And we hope that the science that we are partaking in is able to translate into the community and have effective change. So tonight we are going to be going over a few different things about water quality. First, we will talk about water quality monitoring basics, followed by sampling methods, and then finally developing a sampling method to reach your goals. So after those presentations, we'll have a quick a Q&A session where you can ask and answer all of the questions that you may drop into the chat. So please do hold your questions until after those presentations are finished. So after that Q&A session, we will go into breakout rooms based on the watershed as Rebecca had described. And those breakout rooms will be assigned by Ohio River, the Allegheny River, and the Monongahela River. So do keep active in the chat and let us know which breakout room you'd like to go if you didn't indicate on the survey already. So for our presenters today, we have 3 graduate students at the University of Pittsburgh. We have Becky Forgrave, who's a PhD candidate, will be presenting first. She does a lot of research with 9 Mile Run Watershed Association, and she focuses on quantifying sewer stream connectivity in that watershed. And then we have Marja Copeland, another PhD candidate. And her research examines the hydrology, the biogeochemistry, and the geomorphology of the urban streams. And finally, Tyler Rohan will be presenting last, our 3rd PhD student or candidate, and his research is using a 311-based landslide inventory to figure out landslide susceptibility in the region. So we couldn't do this without them tonight, so thank you all 3 for taking the time, and I will go ahead and stop sharing my screen and let Becky go ahead.
Okay. There we go. Sorry about that. Couldn't get Zoom and PowerPoint on the same screen. Here we are. Okay, so good evening all. Thank you for being here. So I wanted to start with some water quality basics, just talking about the various parameters you can measure, why to measure, and other things. So, okay, so there's an outline of what I'm gonna go over today. I'm gonna start with why monitor water quality, then what to measure, and then moving on to how. So this will start with some existing data and then how to collect your own data, and Marshall will take it away from there. So starting out at the very basics of what is water quality. So you can tell from these two different pictures, sometimes you can tell just by looking at a stream or watershed, you know, if it's healthy, if it's not, but at other times it's not as apparent for how healthy that ecosystem is. And so the definition is water quality would be defined as the measure of the physical, chemical, biological, and microbial characteristics of the water. And so this definition is very broad to encompass all these varying related aspects of stream health. So some of these physical parameters include the geometry of the channel, including things like culverts, but also eroded banks, presence of foreign objects like that tire there. Chemical health incorporates concentrations of nutrients, metals, ions, as well as some emerging contaminant chemicals like pharmaceuticals or personal care products. Biological health is a measure of the organisms living there, their diversity, abundance, and tolerance levels. And then the microbial health encompasses bacteria, viruses, and things that can be present from sewage contamination or other issues. So in terms of why we monitor, water quality gives data to support decision making. And so having data about the state of things in the stream or river can support these decision making efforts. It can characterize baseline conditions. So baseline is just the normal standard conditions for how things are on a day-to-day basis. And that can be helpful to identify trends over time or departures from that trend due to some emerging problem or issue. So monitoring on a consistent schedule over time can be used to identify these issues as they arrive, and then can help direct pollution control efforts to where in the watershed they'll be needed. And then respond to any emergencies or issues that do emerge. You can do that within the monitoring program. So some common chemical parameters to monitor would be temperature, dissolved oxygen, pH, turbidity, conductivity, chloride, and nutrients. And I'll be going step by step through these to provide a lot more background information. And then here is a photo of monitoring in 9 Mile Run by the 9 Mile Run Watershed Association. And they've had a pretty established water quality monitoring program for several years. So starting at the most basic, temperature is just how warm or cold the water is. It'll have seasonal and daily variations that are natural, and then that affects the ecosystem because organisms have very specific temperature ranges that they can tolerate. Temperature will also be affected by tree canopy shading or lack of a tree canopy if the leaves are down, depth of the water, and various inputs such as groundwater or storm drains. Dissolved oxygen is just oxygen gases that are dissolved in the water. It will enter through diffusion from the atmosphere or photosynthesis. So this diffusion happens a lot at these riffles, which are where the water will go over rocks and then incorporate oxygen from the atmosphere into the water. And then at other places, it will settle out, the organic matter and things in the water will settle out and promote decomposition in these pools, and then that will reduce dissolved oxygen. It is measured in milligrams per liter, also known as parts per million, ppm. It ranges from 0 to 10, or percent saturation, ranging 0 to 10%, 0 to 100%. So here's kind of a scale for what the range of dissolved oxygen. Things below 4 are definitely too low to support aquatic life, fish, or most macroinvertebrates. Dissolved oxygen around 4 or 5 ppm, fish can survive for short stretches of time, but not long periods. And then greater than that will just further increase the favorability for fish and macroinvertebrate populations. Some factors that affect dissolved oxygen. So the solubility is just how much dissolved oxygen that water can hold. And it's affected by temperature and salinity. So warmer water will hold less oxygen, as well as saltier water. So algal blooms and the decomposition that results will decrease the available dissolved oxygen, sometimes to the point of no dissolved oxygen, which is anoxia. And hypoxia is just very low dissolved oxygen. Moving on to pH. So pH is a scale from 0 to 14, measuring how acidic or basic the water is. So something very acidic, like battery acid, would have a pH of 0, or something very basic, like drain cleaner, would have a pH of 14. So some other common reference points there, rain is about 5, showing because of the dissolved CO2 in it, where seawater is about 9, a little more basic. Human blood is neutral at about 7, and fish are best in the range between 4 and 9 of pH. So pH is actually a measure of the activity of hydrogen, H+, and hydroxide, OH, ions. So basic is more OH ions, and acidic is more H+ ions. And it is an exponential scale. So 1 pH unit is a 10-fold change. So pH 5 is 10 times as acidic as pH 6. And the pH will affect the solubility and availability of some nutrients and metals, so it will affect other aspects of water quality. So some environmental factors that can affect pH, especially here in PA. There's a lot of industrial legacies here in Southwest Pennsylvania from coal and steel. So slag in that bottom picture is a waste product from steel smelting that they would like dump out molten from these railway cars and let it like cool and solidify on these big mountains of slag. So there's a bunch of these around Pittsburgh. This picture is from West Mifflin, which is apparently the largest man-made mountain. But slag is really basic, about 8 to 10 on the pH scale. So groundwater that will go through that slag pile will come out really basic and then have huge impacts on the water it goes into. On the other side of the scale, mine drainage has a lot of acidity to it from interactions of water and sulfide minerals, creating sulfuric acid. So that can be around pH 3. And it's often noticeable by orange or white precipitates from iron or aluminum coming out of the water when the acid mine drainage mixes with more neutral water. So this picture is from along the Gap Trail. The turbidity is a mixture of how clear the water is. So that is clear to murky. And it is the cloudiness caused by particulates. So individual particulates are usually invisible to the naked eye, but we can see the accumulation of them from suspended sediment. So these two pictures here, both from 9 Mile Run, I think taken about a week apart, you can see just the range of turbidity that a stream can experience. So turbidity isn't necessarily always a bad thing. Like, we don't expect all fresh water to be crystal clear like our drinking water, because algae and sediment are natural parts of that ecosystem. But suspended sediment comes in from erosion and runoff, as well as high flows mixing up the sediment from the bottom of the stream. But really high turbidity will affect the ability of light to get through the water, impacting the photosynthetic ability of algae, decreasing dissolved oxygen, and can clog fish gills. So some factors affecting turbidity, it's usually all inputs event-driven. There's fine sediment washing down storm drains. There's high water flows that erode banks and add a lot of sediment to the water, as well as those high flows will stir up sediment from the bottom. Acid mine drainage can also affect turbidity due to those aluminum or iron precipitates that will come out. So that's that picture on the left, is aluminum precipitates in streets run. There. So these particulates that cause turbidity will stay suspended for a while after a storm event or through faster water, and then settle out in calmer waters like pools or after a while after an event. The conductivity is water's ability to pass electrical flow. So it's directly related to the concentration of ions. So these ions come from dissolved salts and inorganic materials, such as alkalis, chlorides, and sulfides. And more ions means higher conductivity. So ions conduct electricity because of their positive and negative charges when they dissolve. You'll see sometimes conductivity versus specific conductivity. And the difference is that specific conductivity is temperature corrected. And so if you're using a probe that also has a temperature sensor, it will do that for you. The units you see are in microsiemens per centimeter. And so that's that μs in freshwater, and they can get higher into millisiemens in saltwater systems. And freshwater streams are usually about 100 to 2,000 microsiemens per centimeter. So some factors that will affect conductivity: precipitation inputs, road salt, and evaporation. So most freshwater systems have a relatively constant baseline conductivity. So you can see in this kind of conceptual picture here, that's pretty even in normal conditions, but then it will decrease due to freshwater inputs like rain, snow melt, or springs, and increase due to salty or mineral inputs such as road runoff or agricultural runoff. Also throughout the summer, there can be evaporation that can increase conductivity as the water becomes more concentrated due to evaporation. Chloride is pretty similar to conductivity. I mean, conductivity incorporates chloride, but you can also measure it separately. It occurs naturally in groundwater streams and lakes. And since chlorides are the active ingredient in deicers, whether they're potassium, magnesium, or sodium chlorides. Road salts also have some additives like phosphorus and metals, so chloride can be a good indicator that those other pollutants could be present. And it can show up in sewage from water softeners or human waste. So while it is naturally occurring, a high chloride reading, like greater than 250 milligrams per liter, will suggest human inputs. And lastly, nutrients. I'm not going to go too much in depth here because I could really go on and on about nitrogen. And for sampling nutrients, you would need to collect water samples because it can't be done easily with a probe, as Marja will talk about later. And there are some test kits, but they vary widely in their precision and accuracy. But hopefully we'll get a chance to do that maybe another time. This photo is from the Ohio River at Point Pleasant during the 2015 algal bloom. So inputs of nitrogen and phosphorus will promote the growth of algae, and they can get as bad as this picture. And they come in from fertilizer, sewage leaks, pet waste, and erosion. So now that I've gone through all the various parameters, lastly, there is some existing data that you can find. So on this link here to the Water Quality Data Portal, this is a kind of a search function where you'd put in the country, state, and county, and then the site type like stream, or the sampling media like water. And then it will return all of the sites in that area that has that. So here's the existing water quality data that we've got in Allegheny County. There's a lot on the major rivers, but there are some other sites in some of the tributaries. So it's definitely worth exploring if you're looking at getting to data but don't have, you know, a monitoring protocol set up yet. But if you want to get out and collect your own data, Marja will talk about that right now. Thank you.
Awesome. Thanks, Becky. So I'm Marja, and I'll be talking to you about ways in which we can monitor water quality in different watersheds. So as Becky said, there are several things that you can monitor within your watersheds, whether it be temperature, dissolved oxygen, pH, turbidity, conductivity, and so forth. The monitoring can be done using multiple methods, which I will talk about in each of these slides as we go on. You can either use a multi-parameter probe, you could use test kits, or you can just do a lot of the monitoring through visual assessments. And the photo that you can see on the screen here on the left side, that's an example of one of the multi-parameter probes that you can use. And there are several tools that you might need, but this is very dependent upon what we are measuring and the way that we intend to measure. So before I get into ways we can monitor water quality, I think it's important to take a step back and mention that taking notes is one of the best ways that you can have a record of the health of your watershed. So some things that you would record obviously would be the date, the time that we're sampling. You can write who was sampling there, what was the weather, did it rain yesterday or the morning before, are there any strange new smells in the area, what color is the stream, do you see strange things in the stream, you know, whether that be trash or oil slicks, and then obviously the relevant parameters from the probe or any instrumentation that you might use. So on the right here, I have an example of some type of a data sheet that you might have, and then you can make tables that would tell you, you know, at each site, I'm measuring this, and this is the value for that site. So like I said, visual assessments are is a good way that we can tell what's happening within the watershed. So you can talk about water appearance, you can record water appearance. And in this example, it uses a sliding scale from 1 to 10, and you would assign the value to each thing that you've seen. So you can talk about whether or not the water is clear, tea colored, is it cloudy, how cloudy is it turbid, murky in appearance? What are you seeing on the surface? Of course, that's another one that you can record. You can record whether or not you're seeing evidence of nutrient enrichment. That is, how much algae is it? Is there a bloom? Is the water clear? How green is it? Are you seeing like algal mat on top? Those are important things that will tell you about the health of the watershed. And as you monitor frequently, you can see how that changes through time. And these are just some other examples of things that you'd want to note when you're out in the streams. You know, are you seeing grease materials? That's evidence of oil on top? Are you getting a strong sewer odor? Is the water gray, discolored? Last time I was out with Becky, we saw a beautiful trash dryer, which would be another thing that you would note, as that has implications for the health of the watershed as well. Right. So when it comes to instrumentation, there are a lot of different things that you can use. So one of them are colorimeters. These require that your samples be collected. So you collect them into small vials that you can see in the photo on the left, and you would insert them into the machine that would give you a readout of whatever it is that you are seeking to analyze. One of the drawbacks with using colorimeters, though, are they generally require individual reagents, and that can get expensive through time. Handheld probes are a common piece of kit that's used in water quality assessments, and they tend to measure a lot of different parameters, whether that's pH, DO, turbidity, conductivity, temperature, nitrate, chloride. One of the nice things with using probes is that it generally is one piece of equipment that you would just insert into the stream, and that it will give you all of these measurements at once. All right, so let's get into how we would measure each of these water quality parameters. So we can start with measuring temperature. So a standard way to measure temperature would be to use a thermometer. Using a thermometer, you would generally collect the water into a sampling bottle, and you'd hold the thermometer in the bottle away from the sides or the bottom to ensure accurate reading, and then you would record that measure. Or if you're using a temperature probe of some sort, you may want to wade into the center of the stream if it is safe to do so. Place your probe 0.3 meters beneath the surface of the water and wait for the data to stabilize on the readout, and then you record your data from that equipment. You can also measure pH, and pH can be measured in several ways as well. So you can also measure pH using the probe, but generally with probes, it's important to continuously calibrate the equipment. You need to check to make sure that it's calibrated if necessary. And if you're going to collect from the stream, you would once again wade out into the stream if it is safe. Place the probe around 0.3 meters beneath the surface of the water, wait for the reading to stabilize, and then record that reading. If you are collecting using a bottle, you would collect the sample into the bottle and then place your probe in the sampling container. You might want to swirl it gently so that the probe is seeing, getting a full sampling of the water that's within the bottle, and then allow the reading to stabilize once again and record that value. Another way to measure pH is using colorimetric kits, and I think this is one of the things that we probably used in like a general chemistry class at some point. In this method, you would take one of the pH strips and dip it into the water until it's fully moistened, whether that is directly into the stream or if you've collected it into a sampling vessel. You'd wait a couple of minutes for the colors to fully develop, and then you would compare your strip to the chart that is provided with the kit. So moving on, we can also measure dissolved oxygen, and that's generally used, measured with a probe. Your typical range for rivers is here on the screen. It's usually between 8 and 12, 13 milligrams per liter in rivers. If you're collecting directly from the stream, once again, it's the same methodology. You would want to place your probe at a depth beneath the surface. 0.3 is generally a standard that is used, and wait for the reading to stabilize, and you record that before moving on. If you're going to use the bottle, because you don't want to wade out to the stream or it's not safe to do so, you might want to collect it within that sampling vessel, once again placing the probe in the container and allowing it to stabilize before recording the value and moving on. And then the final one that I will talk about here is measuring turbidity. So Becky described for you earlier what turbidity is. And in measuring it, we can do that with one of two ways on the screen here, although I will point out before I explain the Secudis that that's generally used more in lakes than it is in rivers, but I'll explain that one anyway. So the second disc or tube you would insert into the body of water, and you record the depth at which you can no longer see the disc well. Or you could use a portable meter or a sonde once again. So the portable meter, you would collect the stream water into a vial that comes with the meter, and then you would insert it into the device, and that would give you a readout in NTU or FNU of the turbidity of your stream. Or you could use a sonde, if you're lucky enough to have a multi-parameter which has a turbidity meter attached to it. Then once you've inserted that device into the stream, you would get a reading of turbidity from the sensor that is attached there. So there's several useful resources that you can find to help you figure out how best to monitor what might be right for the watershed that you are monitoring. That includes the Citizen Science Library, citizenscience.org, and another great resource, which is one that I used a lot in coming up with this presentation, is ALARM, which is the Alliance for Aquatic Resource Monitoring. So, thank you. Then we'll move on to Tyler, who will explain to you how to make a sampling plan so you can put a lot of this into practice.
There we go. Hi, everyone. My name is Tyler Rohan, and I'm shortly going to go over how to build a water quality sampling plan, just to kind of get you in a mindset, thinking about how to develop these plans, going into the breakout rooms for these 3 different watersheds. So, like Marja and Becky had been previously discussing it during their talks, we have to think about why is it important to properly plan watershed sampling. And one reason for this is that there are many different water quality issues that can be affecting a watershed. If you look at the examples I have here, on the left we have the picture from the Siberian Times that is highlighting high aluminum concentration. We have a picture from the Tigard watershed, which is illustrating acid mine drainage. And then we may be looking for where a point source pollution is located, or what a point source pollution is doing to the water chemistry of the watershed that we're interested in. So really developing and narrowing down a key plan is important to properly planning your water quality sampling plan. So before we get into measurements of any kind, and once we've defined our watershed that we're interested in studying, we need to look into what is the background and scope of our water quality project going to be. Really understanding, what are the water quality concerns in this area? What is the historical context? What research has been done in this past? And based on this information, make clear monitoring goals. And just to elaborate a little bit, especially when looking into what past monitoring efforts have been done in your area of interest, it's really important to understand the whats and the whens of what previous research or monitoring has occurred. Looking into what past parameters have been studied, what were the sampling locations that these were using, what was the frequency that they were sampling at, and really can help both guide where you choose your samples depending on the studies, as well as potentially give you comparison data for study or increase the sampling size based on your goals for your water quality sampling plan. And based on this historical and understanding these water concerns, you can really make decisions on what your game plan is going to be. And lastly, before one of the first steps you should take is really looking at who are going to be the concerned patrons of your water quality sampling study. What are the landowners that are located in the watershed that you're examining? What are the agencies that are responsible for regulation and maintaining the watershed? And also, what are the interest groups? Who is going to be interested in the data that you're going to be gathering? And in what format could they be potentially use this to further their goals as well? So now on to clearly defining an objective. So for clearly defining an objective, I really like this acronym SMART. And for SMART, what it means is defining your objective. It should be specific, measurable, achievable, realistic, and be able to be all of these things in a given time frame. So when we're defining these objectives, we really need to clearly state what our desired outcomes are, what are the water quality concerns that you are looking at, gathering data, what is the information that is needed to support this decision, and then understanding, as Marja went into, what are the different types of analyses that are going to need to be conducted, hence what are their data needs, what standards, and are you going to need comparison data to look at with your study. And again, what I was saying with the patrons, really also it's important to think about who else might be using this data outside of yourself, and also what is the level of accuracy that you need to collect your data at to be usable to meet your desired outcome. So after this, it's important to both select and be able to defend your selection for your study sites. Over to the left, I have an example from the Neponset River, where they were choosing study sites to both look at dissolved oxygen content as well as phosphorus. And when defining your selection sites, it's important to define critical sites that are key to your study. And with these critical sites, work needs to be done in learning. Is there access to these sites? Are there screening concerns? Do we need to define boundaries, as in bracket these sites so we cut full coverage of our watershed? And also thinking about what is the flow going to be like at these sites, and are these selected sites representative of your area of interest? So now on to building a plan to take field measurements. Over here to the right, I have a few example photographs from water quality sampling done by USGS, as well as Angela Mullins, another PhD student in our department. And as Marja listed off in her presentation, there's a ton of different parameters that can be measured. So clearly defining a protocol that can get the measurements for the parameter you're interested in, as well as providing other common fields for other study comparisons, such as what are the hydrological conditions at your site, what are the weather conditions, what is the land use in your area, what equipment are you going to be using to conduct this research, or what issues with equipment you had is equally important, the stream flow and the water depth, and as well proper organization, sample ID, a date, and the time that it was collected. So going a little bit more into scheduling to reach these target conditions depending on your study. Every study depending on, or not every study, but most studies depending on what they're looking at are really going to have critical conditions that are going to need to be met to get proper data to give them outcomes that are what they're going after. So critical conditions are something like, are we trying to look at high flows or low flows? Is there a seasonality to our data? Are there locations that need to be examined in order to reach our desired outcome? And also, if we're characterizing a watershed, sampling at a variety of these conditions to get kind of a wider picture of what's going on in this watershed. And also, as I've stated before, but is always important, making a consistent sampling protocol and standards to look at things such as peak seasons and making sure your study has an adequate sampling size. And always, when doing water quality monitoring, a standard procedure keeps things safer. You want to do proper equipment calibration, and even though you should be knowing your environmental conditions based on your research, it's always important to know the environmental conditions that you will be sampling in. So a last and very important part of your water quality plan needs to be a quality assurance and control for your study. And the four main components of this quality assurance and control are making sure that, before you've done your sampling, that you've done proper equipment testing, inspection, and maintenance, building a good sample identification plan, sometimes using what people have done in the past for good comparison data, making sure you have quality control samples, and then also determining a method for your data, for validating your data. So now that we've kind of talked about these three different aspects, if you guys have any questions for Marja, myself, or Becky, feel free to unmute yourself or just type them in chat, and we'll be happy to answer them before we go into these breakout rooms and build these plans of our own.
Okay. At this point, it doesn't look like we have any questions. Somebody did have a comment that in addition to providing a description of the overall appearance of the stream, it's often helpful to take a picture of the sampling site or other sections of the stream, labeling the picture and placing it into a specific file for sampling data. So thanks for that comment. Thanks to all of you for your presentations. That was great. Last call for questions before we move on. If you want to join in the breakout rooms I assigned as best I could for the information I have. So if you haven't shared with me what your watershed is, please do so now so we can move on.
All right, so I'm going to share my screen real quick again. All right, so we're about to go into our breakout session of this webinar, and the hope is that we can facilitate some great conversation about what you're seeing in your watersheds. When we are grouped into the Ohio, the Allegheny, and the Monongahela for this conversation, but we would really like to know what you see while you're out and about. What are some of your favorite areas? What assets do you see? What concerns do you see? And what potential sampling locations do you see? So those are going to be the three things we'll talk about: assets, concerns, and potential sampling locations. And each room is going to have their own facilitator, and you are going to be sent off here shortly. But just as general ground rules before heading into the breakout rooms, just be mindful of time. There will be probably around 10 people per room, so just be cognizant and please allow time for folks to share their thoughts and opinions of the questions that will be asked. And if you don't have time to answer the question, drop your response in the chat or follow up with us afterward. We'd be more than happy to hear your thoughts or suggestions as well. So with that being said, we will go into these breakout rooms and return around 7:25 to reconvene before we head out. So I will let Rebecca send us off here soon.